difference for sets A and B. We define the difference A minus B, or sometimes we write it like this also, A backslash B, that this symbol, this backslash symbol is said to be set minus. Okay, it's used so far I know only for sets. We define as or to be the set let me write it here. A minus B is the set of those elements of A which are not in B. I mistook this one for intersection. I was thinking of something else. Okay. For example, (1, 2, 3) minus 1, 2, 4. So it is the set of those elements in the first set that are not in the second set. So the elements in the first set that are in the second set are 1 and 2. So 3 is not there in the second set. So this is the singleton set 3. In many cases, B will be a subset of A. When we talk about the difference A minus B, in many cases B will be a subset of A, and we already know from our discussions on knife set theory that in that case A minus B is said to be the complement of B in A. That is not mentioned here, however we know that, okay, but not necessarily. So this is the difference. Now after this there are some basic laws of set theory with which we are already familiar. We have seen them in knife set theory, but nevertheless here there is a proposition, and this is proposition 3.1.28. The name of the proposition is this: sets form a Boolean algebra okay, and the statement is, it goes like this: let A, B and C be subsets of a set X. X is some set in which we have found 3 subsets, say A, B, C, B, any subsets of any set X. Then we have these things. Then the following hold. Minimal element. Recall that result which says that sets are partially ordered by inclusion. So it's a partially ordered set, although I haven't said anything about partially ordered sets. But in the sense that if I have A as a subset of B, then A is in a sense less than or equal to B, or A is not greater than B. A is inside B. In that sense, the minimal element, there is only one minimal element, which is the empty set. And just like that, in the context of this proposition, the maximal element is X, because all the sets A, B, C are subsets of X. So they satisfy this relation. Okay, they are in this relation to one another, A and X, or any subset of X and X. So minimal element, how the minimal element behaves with respect to union and intersection. So it's just this, we already know. A union the empty set equals A. A intersection the empty set equals the empty set. Like that, we can see how the maximal element behaves with respect to union and intersection. Let me write it here. A union X is X and A intersection X is A. The statement that sets form a partially ordered, a class of sets is partially ordered by inclusion. What I'm trying to say is that like that there are other things known as partially ordered sets. In them there may be more than one minimum. We will see these things, okay, when we study partially ordered set. Here itself we will study at some point. We will see that in a partially ordered set, minimum is not necessarily unique. Like that, maximum also is not necessarily unique. For us, in this case, they are unique. Maximal element, then identity. Identity, or we can also say idempotence. I don't really know whether Tao made a mistake here by calling it identity. Note that although Tao's notes are very nice, but there are lots of mistakes. He keeps on rectifying them. He has a blog in which he lets us know about those mistakes, or we can also post indicating that there are some mistakes here and here. If he finds them legitimate, he makes corrections. Okay, so he calls this identity. What we call it is not really that important. The result is important. D. Then come the usual laws, commutative laws, associative laws. Commutativity. Both the union and intersection are commutative operations. Then associativity. They are also associative. Then distributivity. A union B intersection C equals A union B intersection A union C. We express this by saying that union distributes itself over intersection. Just like that, we also have the other thing where we can interchange union and intersection. Intersection also distributes itself over union. A intersection B union C equals A intersection B union A intersection C. Note that the relationship between union and intersection here is, although it looks like addition and multiplication, but it's not exactly like that. In this sense, if A, B and C are three, say, real numbers, then multiplication distributes itself over addition. This has the same structure like this. However, addition does not distribute itself over multiplication. We don't have, what I am trying to say is this. If I have, not this, A plus B dot C, we don't have this equal to A plus B dot A plus C. This in general is not true. But in case of sets, they both the things are true. Okay, so after distributive law, we have partition. Partition involves a set and its complement. It just says that a set and its complement are disjoint and their union is the entire set X, which in knife set theory we will call this X the universal set. And there is one more, the very important De Morgan's laws. De Morgan's laws. So that also we already know. It involves unions, intersection and complements, all of them together. So it says that one of them says that the complement of the union of a union equals an intersection of the individual complements. So this is the complement of A union B, and the individual complements are X minus A and X minus B. This union becomes intersection. That is one. In the other we just interchange this union and intersection. The complement of this intersection equals the union of the complements. I must make sure I haven't made a mistake. No, it's okay. Okay, now there is a remark which honors the logician who is responsible for De Morgan's laws. This is remark 29. De Morgan's law. Okay, my handwriting is getting more and more messy. I don't know why. De Morgan's laws are named after the logician Augustus De Morgan and the time period in which he lived is this 1871. Okay, Augustus De Morgan. He was a logician who proposed these laws. Okay, now it is easy for us because these things we have already proved in knife set theory. So we are not going to do it here. It's already there for us. However, the same thing has been asked in an exercise at the end of this section, that is the sixth exercise. So for us it's done. Okay. Now there is one more remark after this regarding this law. This is remark 30. Note that in the above laws, there is a symmetry between union and intersection. You can see whatever is happening to union, the same thing is happening with intersection, and when they are used simultaneously, we can change their positions also. See? And here of course it is something else, but we can see a rough symmetry between union and intersection, and that symmetry in particular is not available with addition and multiplication. We have seen that one of these distributive laws is true for addition and multiplication, the other one is not. So I am talking about that type of symmetry. And also between the entire set X and the empty set. This is an example of something called duality. Two distinct objects being dual to each other. In this case, the duality is manifested by the complementation operation. See, now does not say anything about complements, but because we know that what a complement of a set is in a given set, that we know what this operation is, which just maps a set to its complement in X. This symbol is maps to. Okay. We will see more about this when we learn mappings and functions. The De Morgan's laws make sure that this operation changes union to intersection. So this operation actually gives us the duality, and also it interchanges the set X and the empty set. I also don't know why Tao made this remark and why suddenly he says of duality. Maybe in future, in some other subject that he discusses, we will come across something where duality is a thing. Okay, then we will know. Now, the statement of this previous proposition, it says that sets form a Boolean algebra, right? And that is named, of course, after the mathematician George Boole. The above laws are collectively called the laws of Boolean algebra, named after the mathematician George Boole, and he was alive in this time period from 1815 to 1864. And these laws are applicable to objects other than sets. Okay, so sets form one example of a Boolean algebra and are applicable to objects other than sets. They play a role in logic, a very important role in the subject of logic. Right. Okay. Now we have seen the axiom of specification, and with the help of that we have defined intersection and we have defined difference. And keep in mind that that fifth axiom allows us to say that the intersection and difference, these things ultimately are sets. These collections are sets. But the axioms we have seen so far, they don't allow us to do everything we need to do, everything we want to do to the elements of a set. One of the things that we would like to do to the elements of a set is this. Suppose there is a set and there are some elements. What we want to take each element, transform it in some way, obtaining some new elements, and we want to collect those new elements and call that collection a set. None of the axioms that we have seen so far, all the 5 axioms, allows us to do this. For that we need a new axiom, and this is known as the, you can probably understand why we need this axiom. We will eventually use it to define functions, or we will use it to define some things, some collections that comes across when we study functions and we want to call those collection sets. That's why we need this axiom. So this is the sixth axiom, and it is aptly called the axiom of replacement. We are going to replace the elements of a set by something else. And the statement goes like this: let A be a set for each element, or let me write it like this, for an element, for any element x in A, and yes, I should write any, and any object y. We are not saying anything about y, whether y belongs to some set or not, that is not clear. Y is some object given to us, and any object y, let Px, y be a property or a statement. Let me write statement, or let me write property itself. Be a property pertaining to x and y. So, like the axiom of specification, in this case also we have a property, but it depends on two things: an element of A and another object y. Note that this object y may be an element of A itself, however, it may not be also, and we don't care about that. The only thing we have here is that x must be from A. One of the objects must be an element of A. So that means for a given x in A and for a given y, Px, y is a statement that will be either true or false. It's a well-defined statement, well-formed statement, such that now there is a condition. For each x in A, there exists at most one object y for which Px, y is true. So each object x in A, if I choose any object from A, I mean an element from A, then corresponding to that element there is at most one y for which this statement Px, y is true. So for a given element of A, I may not have any y. However, if there is a y, then there is only one such y. That's what we mean by at most. Then if this all these things are true, if I have this hypothesis, then this axiom says that there exists a set. What set? Y such that P of x, y is true for some x belonging to A. We already know what this for some means. For some, if you recall from our discussion on mathematical logic, for some actually means for at least one. That is, there is some, at least some x for which this is true. So this axiom says that then there exists a set whose elements are y, such that px comma y is true for some x belonging to A. That is, for any object z belongs to this set is true for some x in A if and only if z belongs to, oh sorry, no, I don't have that. If and only if p of x comma z is true for some x in A. That is, if there exists at least one x in A for which this statement is true. In what way is this axiom replacing the elements of A? In this way, you see. Let us just see what this axiom is saying. I have the set A here, and I have the elements in A. I choose one element, say I take three elements, x1, x2, x3. Okay, suppose this set has three elements. Now, there is a property P such that if I choose x1, then there is an object y1 for which this property is true, and y1 is the only object for which this is true. Also, for x2, I have an object y2, a unique object y2, such that this statement is true. For x3, suppose I have nothing, there is nothing for which this is true. Then this P, whatever it may be, satisfies the hypothesis of this. Then the axiom says that this is a set. The collection of those objects Y for which this is true, this collection is a set. So here we have replaced x2 by the object y2, x1 by the object y1, and we have not replaced x3 by anything. Okay, so that's how from a given set we are getting an entirely different set whose objects may not have anything to do with this object other than these facts. Okay, so that's how we get a new set. So this is known as the axiom of replacement. Now we need examples to illustrate this. And what are the examples? Oh yes, example 3:1:31. Let A be, say, this set, this small set of these three natural numbers 3, 5, 9. Let px comma y. Oh, I have to say this explicitly. For any x in A and any object y, let px comma y be the property or statement, same thing, that y is the successor of x. Because x is a natural number, I am choosing x from A, so I can talk about its successor. Then for each x in A, there exists exactly one y such that Px, y is true, namely the successor of x. So exactly one means also at most one. In this case, every element of A will be replaced by its successor. Hence, Axiom 3.6 says that the following set exists. Set exists means there is the collection that we are going to write is a set. Y such that y is equal to x plus plus for some x belonging to A. And we can clearly see that since we are talking about the successors of the elements of A, this set is nothing but successor of 3 is 4, that of 5 is 6, and that of 9 is 10. So this is a set that this axiom guarantees. Okay. Now we can keep this A same and change the piece